Hello everyone. For today's video, we're going to be learning about our last vector operation of the semester. We're going to be learning about the cross product. Now the cross product is different from the vector operations that we've used previously. So the vector operations that we've done previously are vector addition as well as the dot product. So we're going to be talking about the cross product today, which is a completely different vector operation. Today, we're going to be interpreting and applying the cross product graphically. We are also going to learn about how to do the cross product in a component form, but for this video today, we're just going to be looking at the cross product graphically, and then we are also going to use our new knowledge about the cross product to apply the cross product to a real world situation. So let's go ahead and get started talking about what the cross product is. The first thing that I want to talk about is that even though as we go through the definition of the cross product and we begin to apply the cross product to problems, even though we may see some similarities between the cross product and the dot product, for instance, both the cross product and the dot product are vector multiplication operations, the cross product is fundamentally different from the dot product, and they have several differences that we're going to talk about. The big one that I want to talk about first is that the cross product outputs a vector, and this is different from the dot product. So the dot product outputs a scalar, and the cross product outputs a vector. And this is such a big difference that sometimes the dot product is referred to as the scalar product, and sometimes the cross product is referred to as the vector product. So just to stress that again, while the dot product outputs a scalar, one of the biggest differences between the dot product and the cross product is that the cross product outputs a vector. We should also talk about notation. So why do we say dot product and why do we say cross product? Well, we've talked about the dot product and the cross product may share some similarities, like they are both vector multiplication operations, but they are fundamentally different from each other. Remember, the dot product outputs a scalar, and the cross product outputs a completely new vector. So they are different operations that do different things. And in order to differentiate between which vector operation we're doing in our problems, we should always say dot whenever we're indicating that we're taking the dot product, so vector A dotted with vector B, and we should always draw the dot whenever we write out our work. Whenever we're taking the cross product, we should always say cross, so I'm crossing vector A with vector B, and we should always draw a cross in our work to differentiate, to distinguish between these two vector operations. So the dot product and the cross product are different, so we use different symbols and different language to describe them. We've said that the cross product outputs a completely new vector, but what does that vector look like? How do we describe that vector? So let's do an example. Let's say we have vector A crossed with vector B, and the output of the cross product is a new vector, vector C. So we have our vector A drawn in our diagram down here, and we have vector B drawn tail to tail with vector A. So the first thing that we notice is that whenever we draw vector A and vector B tail to tail, they define a plane. They define a 2D surface. So a good everyday life representation of a plane is like a piece of paper or the surface of a desk, right? So vector A and vector B placed tail to tail are going to define a plane. The output of the cross product, vector C, is perpendicular to that plane. So vector C, whenever it's placed tail to tail with vectors A and B, is perpendicular to the plane created by vectors A and B. So vector C is perpendicular to that plane. Now you might ask yourself, okay, if vector C is perpendicular to the plane, is vector C perpendicular to vector A? And is vector C perpendicular to vector B? Remember that this plane is defined by vectors A and B. Vectors A and B live in that plane. So if vector C is perpendicular to the plane, vector C must be perpendicular to the vectors that live in that plane. So vector C is perpendicular to vector A, and vector C is perpendicular to vector B. So vector C is perpendicular to the constituents of the cross product. Now what about the magnitude of vector C? So the magnitude of vector C is graphically represented by the area spanned by vectors A and B. So the area spanned by vectors A and B in this diagram is this green, didn't draw very well, is this green parallelogram here. So the area of that green parallelogram is equal to the magnitude of vector C. Now this is just a general definition of what the cross product is. We're going to go through each of these steps in more detail in some examples. So what I want to do on this slide is get a better understanding of the graphical representation of the magnitude of the cross product. The cross product outputs a new vector. That vector is going to have a magnitude. That magnitude is represented by the area spanned by the two constituent vectors. So if we do an example, let's say vector W crossed with vector L, and we want to determine what its magnitude is going to look like graphically, we need to draw the area spanned by these two vectors. The first step in doing so is redrawing the vectors tail to tail. So let's redraw vector W and vector L tail to tail. So I have vector L here, so this is our redrawn vector L, and then I have my vector W here, so this is my redrawn vector W, drawn tail to tail with vector L. The magnitude of the cross product is going to be represented graphically by a parallelogram, and vector W and vector L form two sides of this parallelogram. We have to shade in the other two sides ourselves. So let's draw our third side. So if it's the other side of a parallelogram, it's going to look something like this. And our fourth side, if it's a parallelogram, is going to look something like this. So the area of this parallelogram, the area that I'm shading in here, is going to be equal to the magnitude of the cross product between vectors W and L. So the area of the parallelogram is equal to the magnitude of the vector outputted by the cross product. And this is the graphical representation of that magnitude. What if Instead of just looking at the cross product magnitude graphically, we wanted to calculate the cross product magnitude explicitly. So, in order to calculate the cross product magnitude, we're going to need the magnitudes of the constituent vectors and the smallest angle between the two vectors whenever they are placed tail to tail. So I've redrawn vector W and vector L over here, tail to tail, and I've also listed some values for the magnitudes of the vectors so that we can do an example calculation of cross product magnitude. So the definition of the cross product magnitude is vector W crossed with vector L magnitude is equal to the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by sine of the smallest angle between the two vectors whenever they are placed tail to tail. Now this looks similar to how we calculate the dot product, but remember, we are only calculating the magnitude of the cross product right now. We haven't figured out the direction of the cross product. Remember, the cross product outputs a vector. The cross product magnitude also uses sine and not cosine, and these are some differences between the cross product and the dot product. Let's go ahead and plug our values into our equation here. So the magnitude of vector W is equal to 5 units multiplied by 4 units multiplied by sine of 70 degrees. So 70 degrees is this angle here. It's the smallest angle between vector W and vector L whenever they are placed tail to tail. If we simplify this, we see that 5 units multiplied by 4 units is 20 units squared, and sine of 70 degrees is equal to 0.94. The one thing I want to talk about here is the units for the magnitude of the cross product. You can figure out the units of the cross product vector. You can figure out the units of the cross product magnitude from this equation. So the units of the cross product magnitude are going to be the units of vector W multiplied by the units of vector L. And in this example, that's going to be units squared. So the units of this cross product are going to be units squared. And if we simplify even further, if we multiply 0.94 by 20, we get that the magnitude of the cross product is going to be equal to 18.8 units squared. So the final units of the cross product, the final units of the cross product magnitude are going to be units squared, and we have explicitly calculated the magnitude of the vector that the cross product outputs. So I put a note on the previous slides about the properties of the cross product and what we were calculating. Was what we just calculated the whole picture? Do we have all of the information about the cross product by calculating the cross product magnitude? And the answer is no. Remember that the cross product outputs a vector, and a vector has magnitude and direction. What we've found is the magnitude of the cross product's result. We found the magnitude of the vector outputted by the cross product. What we need to define a vector is magnitude and direction. So we found the magnitude. The next step is figuring out the direction of the vector outputted by the cross product. In order to determine the direction of the vector outputted by the cross product, we're going to use the right-hand rule. The right-hand rule utilizes our thumb, pointer, and our middle finger. In the cross product, we place our first constituent on our pointer finger. So we place vector W on our pointer finger. We place our second constituent on our middle finger. So we place vector L on our middle finger. And the resulting vector, the output of our cross product, is going to go on our thumb. So the thumb direction indicates the direction of the vector outputted by the cross product. Remember that the vector outputted by the cross product is perpendicular to the plane spanned by the constituent vectors. So your thumb must always be perpendicular to your pointer finger, and your thumb must always be perpendicular to your middle finger. And your constituent vectors don't have to be perpendicular. The output of the cross product is perpendicular to the constituents, for sure, but the middle and pointer finger, the constituent vectors of the cross product, do not have to be perpendicular. Just like vector W and vector L are not perpendicular, your middle finger and your pointer finger do not have to be perpendicular in the cross product right-hand rule. Okay, let's complete our example of vector W crossed with vector L. We have the magnitude of the cross product that we calculated earlier. The magnitude of the cross product is 18.8 units squared. Let's figure out the direction of the cross product using the right-hand rule. So vector W, first constituent, goes on our pointer. Vector L, second constituent, goes on our middle finger. And the resulting vector, which I'm going to call vector Q, is going to go on our thumb. So we place our pointer finger in the direction of vector W, and we place our middle finger in the direction of vector L, so something like this. And we see that our thumb is pointing into the board. So vector W on our pointer finger, vector L on our middle finger, and our thumb represents the direction of vector Q, and that is pointing into the board. And at this point, we've fully defined our cross product. The cross product of vector W crossed with vector L has a magnitude of 18.8 units squared, and it has a direction of into the board. One of the properties that we explored with other vector operations was the commutative property. Basically, does the order of that operation matter? So with vector addition, the vector A plus vector B is equal to vector B plus vector A. Vector addition has the commutative property. It is able to be done in any order. So what we want to figure out with the cross product is, does it share this property? Is the cross product commutative as well? So the first step in doing our cross product graphically is representing the magnitude of the cross product with the area spanned by the two vectors. So what we're going to look at this time is not vector W cross vector L, but vector L crossed with vector W. For the process of representing the magnitude of the cross product graphically, we redraw the two vectors in the cross product tail to tail. So this is going to be our vector L. So this is our redrawn vector L, and this is vector W. This is our redrawn vector W. So we've redrawn vector L and vector W tail to tail. This is how we graphically represent the magnitude of the cross product. And then we use these vectors to represent a parallelogram. So these vectors represent two of the sides of the parallelogram, and we fill in the other two sides here. And then the area of this parallelogram is going to be equal to the magnitude of the cross product. And you know, whenever you do something graphically, it's not perfect, but we see that this parallelogram, whenever we have vector L crossed with vector W, is identical to the parallelogram that we had previously. So at least as far as the magnitude of the cross product goes, the magnitude of vector L crossed with vector W is equal to the magnitude of vector W crossed with vector L. We've demonstrated that the graphical representation of the magnitude of the cross product does not change when the order of the cross product changes, but drawing things out is always a little bit imprecise. So we also want to calculate the magnitude of our switched order cross product and see if we get the same magnitude as before. So here we have the magnitude of vector L crossed with vector W is equal to the magnitude of vector L multiplied by the magnitude of vector W multiplied by sine of the smallest angle between the two vectors whenever they are placed tail to tail. So I've drawn these two vectors tail to tail over here. We want this angle, which is going to be 180 degrees minus 110 degrees. And then we also have the magnitudes of the vectors given over here. So let's go ahead and plug those values into the definition of the magnitude of the cross product. We have the magnitude of vector L multiplied by the magnitude of vector W multiplied by sine of 70 degrees. And let's simplify that a little bit more. So we have 20 units squared. Remember, we treat units just like we treat numbers. So we have units multiplied by units, which is going to give us units squared as the final units of our cross product magnitude. And the sine of 70 degrees is going to be equal to 0.94. And if we simplify that even further, plug it into our calculator, we see that the magnitude of the cross product we're calculating here for the switched order is the same as the magnitude of the cross product that we calculated earlier. So we verified two different ways that whenever you switch the order of the cross product, the magnitude of the resulting cross product is not going to change. So let's talk about the direction of the resulting cross product. Remember that the cross product outputs a vector. We verified that the magnitude of the cross product doesn't change whenever you change the order, but we need to determine if the direction of the vector outputted by the cross product changes or not whenever you change the order of the cross product. So what we're going to do is we're going to use the right-hand rule. Using the right-hand rule for cross products, the first constituent in the cross product goes on our pointer finger, the second constituent of our cross product goes on our middle finger, and then the thumb represents the direction of the vector outputted by the cross product. Remember, your thumb has to be perpendicular to your pointer and your middle finger, but your pointer and middle finger do not have to be perpendicular. So I place vector L on my pointer finger, vector W on my middle finger, so vector L on the pointer, vector W on the middle finger, and my thumb, representing the direction of the vector outputted by the cross product, is pointing out of the board. So whenever you switch the order of the cross product, the resulting vector direction flips. Whenever we had vector W crossed with vector L, the resulting vector pointed into the board. But whenever we did vector L crossed with vector W, the resulting vector pointed out of the board. So the order of the cross product matters. The cross product is not commutative. It is something else. This is a property we've never seen before. Whenever you change the order of the cross product, the vector that is outputted by the cross product flips its direction. So vector W crossed with vector L is equal to the opposite of vector L crossed with vector W. Remember that we saw the magnitude of the cross product did not change, but the direction did. whenever you multiply a vector by a -1, it flips its direction. And that's what this equation demonstrates here. Whenever you change the order of the cross product, the magnitude of the cross product stays the same, but the direction changes. And this property is called the anti-commutative property. It's the only operation that we've learned that has this property. Both the vector addition and the dot product are commutative. The cross product is anti-commutative. The last property of the cross product that I want to discuss is what happens when you cross a vector with itself. So there are two ways you can think about this. We can think about it in terms of the area spanned by the two vectors when they're placed tail to tail, or you can calculate the magnitude of the cross product explicitly. So let's do the parallelogram method first. So what happens if I redraw vector W tail to tail with itself? And I've used a different color here. So vector W tail to tail with itself, and we want to see if it forms a parallelogram so that we can determine what the magnitude of the cross product is. But these two vectors do not form a parallelogram. They do not have an area spanned. So this should tell us that the magnitude of the cross product is 0. And we will get the same result from calculating the magnitude explicitly. So what is the smallest angle between a vector and itself whenever they are placed tail to tail? It is 0 degrees. So theta, the theta that we're going to plug into our sign here, is going to be equal to 0 degrees. What is the sine of 0 degrees? That is also going to be equal to 0. So the cross product magnitude of a vector with itself is equal to 0. So what do we say when something like this happens? Because the magnitude of the cross product is 0, and a vector is defined by its magnitude and direction, we say that this cross product doesn't exist. It doesn't have a magnitude. A vector has magnitude and direction. The cross product of a vector with itself does not exist. It is equal to 0. So, another thing that you may ask is, what happens whenever you take the cross product of vectors that point in the exact opposite direction? What happens if the theta is no longer equal to 0 degrees, but is equal to 180 degrees? We're going to talk about this more in class, and you can also work through it yourself. Just want to outline the properties of the cross product that we learned today. It is a vector operation that outputs a completely new vector. We can calculate the magnitude of the cross product using the parallelogram method, or calculate it explicitly. In order to determine the direction of the cross product, we use the right-hand rule. The cross product is anti-commutative, so the order of the cross product matters. And something that we didn't prove, but is true, is that the cross product is distributive. During our next video, we're going to apply the cross product to a real-world situation. Remember, all of the vector math and operations that we're learning in this class have real-world applications. And our next video will help us better understand something from the real world called torque.